Yeah.
Okay, well, let's get back going. So, whoever was who was doing this question?
You?
Okay, I was, but I saw that somebody started. No, okay, never mind.
You got two. Yeah.
That stuff was already filled in. Okay, never mind. Let me pull up the exam again. Okay, so before I was interrupted, uh, this one is like the problems that you've seen before on exam 2, 3. I don't know if it was on exam 2, but I know that it's definitely on exam 3. So we're going to start over reading again, but I want to approximate how many instructions are to be executed for each of the classes. Calculate the total number of cycles for each class and the overall total cycles for all classes. Calculate the percentage of total cycles by each class with respect to overall total cycles. Addition used for calculating memory address for load store instructions should not be considered, but loop count increment should be considered. Okay, let me make sure that it started. Alright, so this one's actually not that bad. So we'll start with add. I'll highlight all the adds. Highlight and do yellow. So this is an add right here. Then we have add, and then that's not the right color. And then add. Then wait, am I missing something? Addition used for calculating memory addresses. I saw that. Okay. So we're gonna do. So we have 3 adds right here. Then we have. I don't know if he wants us to consider this as an add or not. I think I saw that he put down 5.
Yes. So what he considers is he uses 2 add operations to find I minus 1 and
Okay.
I plus
I
1.
didn't know if that counted as memory address. Okay.
Yeah.
So add here, and then add here. So, like I said, this being an add is just because it's just adding a negative. So right now we have 5 adds. Load store. We're not going to count these because these are very minuscule, even though you are loading a few things. So we have this as a load. Let's change this to blue. Load, load, and then one final load. So we have 4 load stores. And then branch. For the only branch we have here is our for loop. And so whenever you see a for loop in code, then you can assume that it's just going to be 2 branch instructions. So one to check the case and then one to bring it back. So pretty straightforward. Now to get the number of cycles, you do your instructions times CPI. So we will do 5 times 2, 10, 8 times 4, 32, 4 times 2, 8. So he wants total cycles. So total cycles it's now going to be, so it's 40 plus 10, that's 50 times 10, 3. So that's how many total cycles?
A quick question.
Yeah.
So I've missed this portion of how did you calculate the number of branch instructions?
So we're looking at the code and we see that there's a for loop, and this whole class up to this point, I've always said, whenever you see a for loop, because you just want to assume that that's going to be 2 branch statements, because you have a branch that checks the case, and then you have a branch that jumps back. So I think Christian had, yeah, so you have this BEQ down here, which goes back to the loop, and this BEQ up here, which checks the case for the loop to see if it's met the case. So you have 2 branches.
I see, thank you.
Yeah. Cycle percentage. This one's pretty straightforward because they gave us pretty easy numbers, but you can just leave them all as fractions. So does this want us to calculate for anything else? Calculate percentage. Okay, no, that's it. So this one's pretty straightforward. It's a lot simpler than any of the ones you've had like this so far. So yeah. Any questions?
Yeah, I got a question.
Mhm.
Why is n-1 and the for loop condition, why does that not count as an add instruction?
That is a good question. I would calculate.
If you use add-I with like a negative number, so it would count just like an add.
I think that would just be because like that would just like be one like add instruction out of like the 1,000 iteration that there'd be. Because like you kind of have like one add right here and then 2 add right here. Like so that's 2 adds, like 2 add instructions being executed like every like for 1,000 times. So that does count. I mean the n-1 would count, but like that's probably like really insignificant, I guess.
Yeah,
I think that's why.
because
That's just
the
like
way you would have to put this, you would have to do the n-1 before you did this BEQ statement right here.
Yeah, that's what I was thinking.
So, because I was thinking about counting that too, because I was looking at his and I saw that he put 5 down. So I was like, wait a minute. But yeah, what Christian said.
Okay, yeah, that makes sense.
Okay. Any more questions? Okay, I'll hand it off to Zach and we'll do 3.
I'm not watching the stream. Are you over the question?
Tengo mi estoy en un review session, pero estaba viendo en mi espalda que estos pelos salieron de mi espera, tengo que asegurarme que no se dice.
What'd you say? I'm over the question. Like,
Yeah.
My screen's on it.
So this is what is the CPI for each implementation and which implementation is faster. So we're going to have to find the CPI and the CPU time of each question. So this is what we've been doing since test 1. I think there's a question like this on test 2 as well. But first, you got to remember that the equation to find CPU time is instruction count, that's that, times CPI, times, what is it, clock rate, cycle time? He is calling these things weird things. The answer is cycle time. Cycle rate. Clock rate, probably. Either way, because we have a clock rate of, I know, I don't know why I called it that. Okay, so that's our equation. So as you can see, we have all of those listed out for us. So for P1, we have CPI of clock rate, CPIs of 2, 8, and 3. And then we have clock rate of 4.0. And then the global instruction count is 1 times e to the 6. So I'll put that down later. So P2 has CPI of 1, 10, and 8. And the clock rate, see if I can find it, it's 3.8. Okay. So then we have the global instruction count of 1. And it's going to be 1 times 10 to the 6, but for now we'll just keep it simple. All right. So we got to add up all of our CPIs. And so we're given percentages for each one of the classes. So for the ALU, it's going to be times 0.4. Load stores times 0.3. And the same thing for class control transfer instructions. Okay. And guess I'll solve it. I don't really want to. 0.8. Oh dear. 8 times 0.3. 2.4. That's 0.9. All right. Now we can add up all the CPIs. 0.8, 3.2, 4.1. Just in my head. Hopefully that's right. Same thing with CPI is the CPI of implementation 2. Multiply each of the CPIs by the percentages. So times 0.4 times 0.3 times 0.3. This one's a lot easier. 0.4, 3, not 0.33, and 0.6. Doing this in my head real quick. It's 4. Okay. So now we can actually, so I guess I should highlight these since these are, it does ask you what the global CPI is. So global CPI P2 and 4.1, the global CPI for P1. All right, now we can do the CPU time. So the CPU time for P1 equals just our instruction count, which is 1 times 10 to the 6. See if I can make this readable. Times our CPI, 4.1, times, cycle, that's why you had it. Okay, so cycle time, we're guessing the inverse of clock rate. So it's going to be instruction count times CPI divided by clock rate. So, and then we do our divided by 4.1 And then CPU time of P2 equals 1 times 10 to the 6 times 4, which is our global CPI for P2, divided by our clock rate. Did I mess this up? What's the, this is 4. And this is 3.8. Okay. We should color code this. Clock rate. Okay, so instruction count is 1 times 10 to the 6 times the global CPI of implementation 1, which is 4.1, divided by the clock rate of implementation 1, which is 4. P2 is the instruction count, which is 1 times 10 to the 6, times the global CPI of implementation 2, which is 4, divided by the clock rate, which is 3.8. Okay. And clock rate is in gigahertz, so it's also by 10 to the 9. And probably safe just to leave it like this. 4.1 divided by 4. I mean, but I'll solve it out. But if you can't do it, just leave it like this. This is fine. But for CPU time for P1 is going to be 1.025, and then CPU time for P2 is going to be 1.05. And these are times 10 negative 3. Okay. So highlight yellow. These are 2 CPU times, and it does ask us to compare them. Oh, that's not correct. Okay. So we have 1.025 and 1.05. And so the smaller number is going to be the faster one. So the faster implementation is going to be P1 because it's smaller. So still highlighted. Okay, this is interesting. P1 is faster, 1.025. It's smaller, which means it's faster than 1.05. And so that's it for this question. But hopefully if you can't do the math, you can still see that 4.1 divided by 4 can be smaller than 4 divided by 3.8.
Any questions on that one? Okay. How did we end up doing this one last time? Did I end up saving this on like MS Paint? You remember?
You didn't MS Paint when you just copied it over last time.
Okay. I'll save the image. Okay. What's Paint 3D? Okay. So this one, the following diagram shows the data path and control signals of a standard 5-stage CPU design for load, store, arithmetic logic instructions. Highlight the data path used for the instructions. Store. Also, we're doing a store word instruction with the format store word RS2, RS1, immediate. Then operation is performed as memory of register RS1 plus immediate equals register RS2. To draw the MS word, okay, so now we'll go ahead and get to this. So let's see. So we have an RS1 and we have an RS1 and we have an RS2. So we'll have one here. We'll have one here. But we will also have an immediate, so we're going to have to go down here. That's a great line. Okay, so for this one, you have two different things happening. You have the arithmetic for solving the address, and you have the actual writing to memory. So what's going to happen in the ALU is going to be what you store, and we're adding the immediate, so that's going to be right here. We're adding this, and we're going to add this to get our address, which will go out of our ALU result into address. Now, what's an RS2 is going to be what is stored into memory. So with a different color, we're going to put this down in memory, and then that just turns into flagging this that we now have something to write back. So it's pretty straightforward. You handle the add for our with the addresses, which takes in RS1 and then our immediate, and then write what's an RS2 to the address, which is solved for through the ALU. So that is all you need to do there. This one is pretty straightforward. Any questions? I'm going to save this. Okay. I'll take that as no questions. Okay. That's all you have to do for that one. That one's pretty straightforward in comparison to the other ones we've had in this class. So, especially, I think the one on the last exam was harder, from what I remember. Okay. Who wants to do the next one? Christian, do you want the next one?
Yeah. Because I think Zach did
Yeah.
this one. Okay. All right. So for this one, it says given the following CPU diagram that you use for your homework 4, you'll be asked in the same way as question 2 of homework 4. So given instructions being executed on the CPU, fill in the table with values for the selected data path for each instruction when being executed on the CPU. So they kind of give you like this big old data path picture with like a table and like the memory values and the memory addresses. And so you're gonna need both of these tables, so that you can fill out the table. And so to kind of start off on the big table there, where it says like it has like all the types of instruction. So that could be like sub1, x1, x5, and x4. We'll go ahead and let me see if I can make this. Nope, that's not. Okay, so so for RS1, it's going to for RS1 it's going to be this x5 right here. Since that's where the RS1 is for the sub instruction, then we'll go ahead and for RS2, that's going to be the 4, since this is your RS2 instruction number. And then for RD, that's going to be 1, since that's the RD for this specific instruction. And so with just like RS1, RS2, and RD, we're just getting like the specific register numbers and then putting them into the table. Okay. And so then now we have like the sub x1, x5, or I guess we're trying to get like the RS1 value. So we'll need to go up to the table. It says that the register number is we'll go down to 5, and then with a value value there is going to be 12, and so we'll put 12 right here. For the RS2 value, we'll go back to the table where it has a register number and a value, and in this case it's going to be 24. Then for the ALU in 2, if that's going to be like the specific data path that's going like that so the specific second input for the ALU, the RS1 value, it already has like your ALU in 1, and so then for your ALU in 2, that's just going to be your RS2 value going right into that. And so then with the ALU in 1 and the ALU in 2, the ALU is going to do like a specific like our arithmetic thing, our arithmetic like operator. So that's like plus, minus, and then there's like one more there, but in this case we're going to be doing subtraction. So so in this case we're doing ALU in 1 minus ALU in 2, which gives you -12. So in the next column we don't need a memory out, since that's mainly for the load word. For write back data, that's going to be your -12, and for the PC next, in most cases we'll just add by 4 to get 16. So for the add I, it's a similar motion where your RS1 value is going to be this x2. We don't have an RS2 value in this add I instruction, since you have an RS1 and then an immediate. And so your RD is going to be 6, since this is the specific register value. And so for your RS1 value, that's when we look in the table for RS1. In this case, when we go up, that is going to equal out to be 32. And your RS2, so and then the RS2 value, we don't have an RS2 value here. So let me see if I'm doing this right. Because your RS1 value. Oh no, my bad. So so I was looking at value 3 or register number 3 that contains 32. In this case we the RS1 value is actually 16. Okay. And so then for your ALU in 2, since we don't have an RS2 value, that's where the immediate value is coming in instead, and kind of like in place for that to go into the ALU input 2. So that's where we'll need 14 for that. The ALU instruction, we're going to have the ALU op to add. So 16 plus 14, that equals 30. And we don't need a mem out. And then for write back data, that's just going back to the RD. We'll go ahead and increment by 4, and that's your P. And your PC next going from 16 plus 4 is going to equal out to be 20. Okay, so and then so then I'll go ahead and kind of so then in this case your RS1 value, that's 4. Your RS2, we don't have an RS2 value. We just have an RS1 and an RD in the specific load word instruction. For your RD, that's going to be 2. Look in the table for your RS1 value, that is going to equal out to be 24. We don't have an RS2 value since we don't have an RS2. Your ALU in 2, that's going to be this immediate value right here again. So that's going to be 14. Then in this case for your ALU in out, or for your ALU op, you're gonna end up adding for this one, just because you kind of want like the specific memory address for like fetching like the specific for where this is specifically located. You kind of grab the contents of that. That's kind of like what a load word does. And so then we'll add up 24 plus 14. It's going to equal out to be 38. And so then if you look in the memory address table, this is kind of like where you want to go here. So your memory address is at 38 and the value is 140. So in this case, your mem out, that's going to be 140. Since we're getting that from the memory, the write back data is also 140 because that's kind of like the specific value that we want. Your instruction address is 20. So we'll just go ahead and add 4 to that, and that's 24. 20 plus 4 equals 24. Okay. And so now for RS1, this is 3 because of this, and then this is 5 because of this RS2. And this store word doesn't have an RD, it just has an RS1 and RS2. So in this case, we'll put an X in this bit. And then for RS1, that is going to be 32 in this case, as we said before. Let me go to the table. Register number 3 corresponds with value 32. Your RS2 value, that's going to be we're gonna go with the 5. Register 5 that contains the value 12. And so then let's see, your ALU in 2, that's going to be your immediate number. So that's going to, in this case, that's -8. Then we'll kind of take ALU input 1 or ALU N1 and the ALU N2 and do the addition so that we can get do an addition in this case.
Wouldn't the RS2 value be -8, or did I see something incorrect? Oh, never mind, I see it.
All right, yeah,
My bad.
sorry. Yeah, and so in this case, 32 plus -8, I guess that's going to turn out to be 24. We're not affecting anything from the memory, nor do we need anything from the write back data since there's no RD. And then 32 plus 4, since we're incrementing by 4, that's going to equal out to be 36. Okay. Now it's time for the BEQ. This one's always a little bit weird. Where like if like x6, where like if the branch condition is true, then we need to use this formula. That's PC plus label times 2. And so then and so keeping that in mind, we'll kind of go start this row right here. So your RS1 value, as kind of we said throughout many of these rows, is going to be x6 because of the register number. The RS2 value, that's going to be 0. Because of this number, the RD, we do not have an RD because branch statements only require RS1 and RS2. Your RS1 value for register 6 is going to be 0. It's going to be 0. Then RS2 value is going to also be 0. And then going into the ALU input 2, we're going to put in 0. And then we're going to go ahead and subtract 0 minus 0, which equals out to be 0. And we use a subtraction in this case to see if both numbers are equal. And if both numbers equal out to be 0, in this case it is 0. We need to actually use the branch target address, which is PC plus label times 2. So in this case, that is 48 plus 4, or your label is going to be this third term right here. That's 4 times 2. And so 48 plus 8, that equals out to be 56. And for this, we don't need a memory out because that's only for the load word. For write back data, we don't have an RD, so that's also an X as well. Okay, I think that should be pretty good. I think I should be pretty much finished. Does anybody have any questions? Yeah. I think there's gonna be 9 that they're gonna have questions on. But maybe.
Yeah, I think everyone's just patiently waiting for number 9 to roll around.
All right. So I guess we'll go ahead and kind of move on to number. I think it's number 6. Yep.
Yeah. This one's gonna be a little awkward. I'm gonna need to keep scrolling back up to the picture. But so number 6 is based on the diagram above, fill in the following table by setting the value 0 or 1 for each control signal. And then for ALU operation, you only need to write down the word for the operation. Okay. So first we have add, and you should know the format for add is RD, RS1, RS2. And since it has a register destination, that means it writes to a register. So that's 1. And so ALU source. So if you were to look at the picture up here, the ALU source signal is basically the multiplexer that selects whether we're getting an RS2 value or an immediate value. So if we're getting RS2 value, then ALU source will be 0, and if we're getting an immediate, ALU source will be 1. So this is an add instruction, which means we have an RS2, so the ALU source will be 0. And here we have an ALU operation. It's add. So real quick, the 4 ALU operations you'll have are add, subtraction, and or. I think we'll see all of them, but and in this example. And so add instruction does not read from memory, nor does it write to memory, nor does it take anything from memory and put it into a register. So we're going to move on to add I. And so the format of this instruction is RD, RS1, and immediate. So it has a register destination, so we're writing to a register. In the ALU source, we're generating an immediate here, so that means the ALU source will need to be 1. It's an add operation, and it does not read from memory, does not write to memory, and it does not take anything from memory and put it into a register. So here we have an OR operation, and an OR operation is just going to follow the same syntax as an R-type instruction. So RD, RS1, RS2, and you can expect it to work similarly. So it has a register destination, so it writes to a register. The ALU source is 0 because we have an RS2. The ALU operation is OR, it's one of our 4. And it's an R-type instruction, so it does not read from memory, does not write to memory, nor does it take anything from memory and put into a register. Okay, so now we have a load. And so the load is register destination, the immediate, and then the RS1. So because it has a register destination, it writes to a register. And the ALU source is 1 because there's an immediate that we use for the offset. And the ALU operation is add because in a load operation to calculate the memory address, we take the offset and we add it on to the base address. And so load does not read from memory, but it does. Oh. Yes, it does. It does read from memory. It doesn't write to memory. That's what I was thinking. Okay, so it reads the memory and writes it to a register, but it does not write to memory. So we have a store, and the store is RS2, immediate RS1, I think. So there is no register destination, so you're not writing to a register. And we have an immediate, so ALU source is 1. And the operation is add, because once again, we're taking the immediate, the offset that's designated by the immediate and adding it on to the base address. And so store does not read memory, but it does write to it. And there is no register destination, so well, we can just, it's a 0. So branch. A branch is RS1, RS2, and the immediate or the label. So we're not writing to a register. We're not generating an immediate because we have an RS2 value. And for a branch, we're subtracting to see if the two numbers are equal in this case. And we're not reading from memory, we're not writing to memory, and we're not putting anything into a register at all. So that one's an X. And that's the general gist of it. I think the only one that's a little bit awkward is the ALU source. And it's just, if there's an immediate value at all, the ALU source will be 1. And if there's no immediate, ALU source will be 0. Do you have any questions about this one? Okay. You want to move on to 7?
This is like, can't remember, somewhere 5, right?
This is 4.
4. Okay. Sounds like homework 4. So they give you a big table. You gotta finally get it crammed onto here. So part A is fill the following table about raw dependencies between 2 consecutive instructions, and also mark the raw dependencies that are load use. You do not need to use all rows of the table. Okay, so they give us the first one, which is add I, x2, x0, 128, and then this load word. Next one, they start with load word x5, and then we use x5 right here, right away. So this would be a load use because we are using x5 after loading it. Immediately after loading it, we're trying to use x5. Okay. Next one, right here, add x7, x4, x5, and then this one. The variable, the register in question is x7. This is not a load use because we're just doing some arithmetic and then using it right away. And then the next one is actually this one again. So x6, well not x6, x8, x7, x6, and then store word. The register in question is x8. Those are all your raw dependencies. So this looks kind of funky on here. So for part B, you are going to map it out using no forwarding. So there was a dependency between here and here, with x2 being that, so you have to have a cycle delay. Now, there's a load use right here, so you have another 2 cycle delay. Then you do not have a dependency between this line and the line above it, so normal. You have a dependency here with x7, so I'm going to try the x. You have a dependency here with x8, and then no dependency here. So pretty straightforward. Now, we're going to do the same thing, but for full forwarding. Full forwarding, you don't have a cycle delay. It gets rid of the cycle delay on a load, on ALUs, which is when you use an ALU statement, so add, subtract, yada yada yada, and then try to use the register that you write to immediately after. You have a 1 cycle delay for a load use, and a still 2 cycle delay for a BEQ. So really have 1 load use here, and that was between this statement. So the rest of them are just going to be no cycle delays, except for the load use, which was between these 2 lines. Okay. And now the rescheduling is pretty straightforward. All we have to really worry about is our load use. So we start with our add I. Now what lines do we have first? This one right here has no dependencies, so we can put that there, and then the rest of it will just follow in suit normally. So store word. I'm sorry, I'm going all over the place. So to get around this, what I ended up doing was just moving this x2 because this statement really has okay. So I moved this statement right here to there, but then I also accounted for me adding x2, well 4 to x2 earlier, by subtracting 4 from the immediate in the store word. So this should solve your problem when it comes to scheduling. And then that gets rid of all of your cycle delays. Okay. Pretty straightforward. Any questions on that one? Okay, cool. So I guess we will move on to question 8. Who's taking question 8? Christian? Sandy?
Yeah, I'll go ahead. Because I think with question 9, I think Zach has like a really good explanation for like how to do this, how to do like number 9B.
Okay.
Better than 9. So,
Okay.
Number 8, it's saying a direct mapped cache has 128 entries of cache lines. Each cache line contains a tag, a valid bit, and an 8-word data block. Each word is 4 bytes. And then it says here we'll need to calculate the number of bits of each field and the memory address that are used to address the cache and the value of each field for memory address. With this whole thing, and then we have to provide the answer in the following table. Okay. So I guess the first thing to do, I'll kind of start out with a number of bits. And so with I kind of have to start with a byte offset. So it says right here that that each word is 4 bytes, right? So that's going, and so another way to say that is 2 to the whatever power equals 4, which equals 2. So before I go on, does anybody like have any questions about this? Because it's kind of it's really important, kind of going on onto like finding anything else.
I didn't get that part at all. If you could get over it.
So it says here that each word is 4 bytes. Do you want to know like the byte offset? So like we'll kind of have to look here to kind of start out to kind of get the byte offset. And then so then 2 to the 2 power equals 4, the 4 bytes, and then we want this specific 2 in our exponent. Like we want the specific exponent, and we want to go to put like whatever's in the exponent into the byte offset. If that makes sense. Yeah. All right. So that now we'll move on to the word offset. Word offset, that's going to be this bit right here, the 8-word data block. And so in this case, that's 2 to the 3 power, which equals 8. So 2 to the x power equals 8 is kind of how you kind of need to start thinking about it. And so then for the word offset, that's going to equal out to be 3 because of this exponent. And so then for the block index, they basically kind of tell you right here where that's 128 or 2 to the 7, 2 to the 7, or 2 to the x. And so then we want that exponent, so that's 7, and then the tag is going to be the rest of that. So that's like so it's like 32 minus all this, so that's 12. So then for the tag, we'll allocate 20 bits to go in there.
Oh wait, how did you calculate the block index once again?
So
Oh,
Or-
is it that exponent up there? 2 to the power of 7?
yeah. The block
Okay.
index is this. Yep. Okay. And so and so then we'll go ahead and get like the specific allocate like specific bits for the specific like hexadecimal. And so then we know for a fact that I think that like each hexadecimal is 4 bits, right? So we can allocate. So the first 20 bits is going to be might be is going to be 0x, and then this. So remember that each hexadecimal is 4 bits. So then we'll need 5 hexadecimals in the tag. That's 4, 8, 12, 16, and 20. So 20 bits. And so that works beautifully in our favor. However, going to like these next few bits is gonna that's where everything like it gets gross, I guess. So for the block index, like we'll need to allocate like 7 bits. And so that's going to be like 8A. And that equals out to be, what is that? That's 0, 0, 0, and then we want 1, 0, 1, 0, but we only want those 7, right? So 7 bits allocates and goes to here. So then for the 5, that equals out to be 0. That's 8, 4, 0, 1. So then we need 3 bits for the word offset. So then it's going to be this 0, 0, 1, and then the last 2 bits, that's going into the byte offset. So does anybody have any questions on this part?
Yeah. So how do you know the number of bits is 32? Is it because of the A word data block and each word is 4 bytes, so that's why it's 32?
So I guess you're asking like why we need like 32 bits within here.
Yeah, so why is it that 32 bits and not 64 or 128?
I think it should just be this memory address, like 0, 0F, A, B, C, 8A, 5. And so like since we know like for the hexadecimal, that's like each hexadecimal is 4 bits, and there's 8 numbers here. That's where we need like 32 bits.
Oh, okay. All right. Thank you.
Yep. Okay. So now we're moving on to part B. So how many bytes are required for each cache line in this cache? And so for this one, you kind of have to like pay attention to like what to the problem and what it's asking. And it says up here that each cache line contains a tag, a valid bit, and an 8-word data block. So we need 20 bits for the tag, since that's kind of like what we got up here, plus your 1 valid bit, or 1 bit valid. Okay, and then and then we want to know the total amount of bytes that are in each like cache line, right? So we know that each cache line has the 8-word data block. So 8-word data block times each word that has 4 bytes. So 8 times 4 bytes. So 8 words, and then each word has 4 bytes. So 8 times 4. So that's 8 times 4. Does anybody have any questions on that?
So back up to the table. How do you determine the tag count again? Because when you wrote down 20, I was confused on how you got it.
So at this point, like at the point of so I kind of went like from like byte offset, word offset, and block index because like I kind of because that's kind of like the ones that are pretty much like given in this. Like we kind of have to figure that out. The 20 bits, that's kind of like what's left over.
Oh, so you just said you add up the 3 numbers before and subtract that from 32, basically.
Yep.
I see.
Okay, so and so then this is, and we'll go ahead and add this up. This is 21 bits plus 32 bytes. Honestly, like so 20 we need to convert this into bits. I think for this one, like how do we do that? I think because I think for this one you can just round up because you're gonna have to divide by 8 so that we can convert back to bytes. You can convert to bytes. I guess for this one you can kind of go ahead and like round up. So because 21 bits divided by 8, that's going to be like close to 3. So that's kind of like where the 3 bytes comes from. Plus 32 plus 32 bytes. That equals out to be 35 bytes needed for each line in the cache. All right. I think I should be good to go. Does anybody have any questions? All right. I guess we'll go ahead and move on to another problem.
What is this, 9? Okay. So 9 similar to what you guys have for the lab. Okay, so for the following C code, it's a 2-dimensional array, and an int is 4 bytes. What you need to get out of that. And then for part A, it wants you to list the variable references that exhibit temporal locality and those that exist spatial locality. Okay. So temporal locality is when you access the same variable over and over. And spatial locality is I don't know how to explain that part, but it's where the cache, when it loads something into the cache, it will fill the rest of the cache block with the elements that are stored at the memory addresses that succeed the one it just accessed. So when you load something into the cache, it fills the cache block with the other variables that it thinks is relevant. The CPU that loads into the cache. So a good spatial locality is when you load all those variables into the cache block and then you actually use them. There'll be an example lower down. So I'll wait to answer the spatial locality question, but for temporal locality, it's what variables are we going to access a lot. And so in part B, it tells you that n is 1,000. So when we look at this for loop, we can see that the topmost loop is going to run 1,000 times. And for 1,000 iterations to the loop, I is going to remain the same. So we are going to be accessing I a lot. I exhibits good temporal locality. And same thing with the second loop. J is going to run 1,000 times before it iterates. So we are going to be accessing J 1,000 times each time we go through the loop. So J also exhibits good temporal locality. And finally, we have in the inner loop, we have sum. Now sum never changes. It's only being added to, or well, okay. So like the address of sum never changes, only the value changes. So sum is going to be accessed a lot when we're going through the loop. It's being stored into, or we're storing into the same address for sum. Okay, if you want me to re-explain that better, please ask. But I said I'm going to skip the spatial locality until I've filled out the table for part B. But so assuming we have a cache that has 2 forward cache blocks, and each cache block can fit 4 integers. So that's what you want to know, is that each cache block can fit 4 integers. So when we try to load something in, we're going to load in an integer, and then it will also load in the next 3 integers to fill out the cache block for a total of 4 integers. So we'll see that later. And so A, B, N is 1,000. So we want to fill in the table for element access, cache miss hit, stride, number of memory access, number of misses, and the miss rate. And A and B are perfectly 16-byte memory aligned, so that just means that they can fit 4 integers. And the cache blocks are initially empty. So we're just going to be focusing on the inner loop. So that's just J. And so for element, we're starting at the beginning. So A of 0, B of 0. So they both start at 0 because I and J were both starting at 0. So, and each time you try to access an element for the first time, it's going to be a miss. And since this is the first time we're trying to load A and B, they're both going to be misses. So now J will increment through the second time through the loop. And if we go up and look at the for loop, we can see that in A, J is being added on to A times N. But in B, J is being multiplied by N as well as being iterated. So what that means is for A, J is going to be iterated by 1. A. So A of J is changed by 1. And because we missed an A of 0, it loads in like A of 1, A of 2, A of 3 to fill out the cache block. And so this one's going to be a hit. But for B, J is being incremented by 1 and then being multiplied by N. So with the stride, it's going to have a stride of N. So we're going to have B being multiplied by JB multiplied by N. And because we've multiplied it by N, all those things we've loaded into the cache block, we've basically just gone over all of them, and we need to reload in B of N. And so that's basically just going to be the pattern for this. So when J is 2, it's going to be A of 2. And we loaded in A of 0, A of 1, A of 2, and A of 3. So this is still going to be a hit. But now for B, when J is 2, it's still being multiplied by N. So now it's 2N. And once again, it's just going over everything we've loaded into the cache block. So it's going to be a miss again.
Could you scroll down? Because right now it's hovering above like the top of the chart. There we go.
And so when J is 3, we're going to have A of 3. And that's still in the cache, so that's going to be a hit. But when for B, since B is being for J is being multiplied by N, for B, it's going to be J is 3 multiplied by N. Once again, we're just going over everything we've loaded into the cache. We have to load this value in again, so it's a miss. But when J is 4, we have now passed everything we've loaded into the cache block. So at A of 4, we're going to have to, it's going to be a miss again, and we're going to have to load in A of 4, A of 5, A of 6, and A of 7. That's going to be in another cache block.
Wait, so why is that a miss again?
So a cache block can fit 4 integers, and when we missed with A of 0, we loaded in A of 0, A of 1, A of 2, and A of 3. Those are so a cache block is filled with those 4 integers. And so when we go for A of 4, it's not in the cache. So it's a miss. But when A of 4 misses, it's going to load A of 4, A of 5, A of 6, and A of 7 into a cache block. So I'll just go ahead and do this one. So when J is 5, we've loaded in A of 4, A of 5, A of 6, and A of 7. So this one's a hit once again. And that's the pattern. Since a cache block is going to fit 4 integers, it's going to miss the first time, load in the 4 integers, and then we're going to hit the next 3 times, and then it's going to be a miss again. But going back to B, when J is 4, it's going to be 4 times N, and it's going to miss again. And the pattern holds true for when J is 5, it's going to be 5N, and it's going to miss again. And it'll do that for all 1,000 times. So if we look at A and B, we can see that each time A is only changing by 1 because J is only being incremented by 1. So the stride is 1. But for B, B is changing by N each time. So the stride for B is N. And so for both of these, N is 1,000, so the loop's going to run 1,000 times. So we're going to try to access it 1,000 times. And so when the stride is N, we're always going to be missing because we never load into the cache block the values we need. So even though we access B 1,000 times, we're going to miss 1,000 times as well. And that gives us a miss rate of 100%. And so for A, so A has the pattern where it's going to miss the first time, load in 4 integers to fill out the cache block, and then miss the 3 times. And it's just going to be that same pattern 1,000 times. So that's easy because 1,000 is divisible by 4. So you can just look at a single group of 4. So misses once, hits 3 times. That's 1 out of 4. So it misses 250 out of 1,000 times for a miss rate of 25%. And so to go back and answer what has good spatial locality, for B, B has awful spatial locality because it misses every single time. Because when we try to load in B of 0, B of 1, when we try to access B of 0, it loads in B of 0, B of 1, B of 2, and B of 3. But then we multiply it by N, so we want B of 4, which is a miss again. But for A, we're going to miss A of 0, and then we're just incrementing by 1. So we get A of 1, A of 2, and A of 3 being hits. and then it's another miss. So B misses all the time, but A, because it loads in the values that succeed the ones we miss, it fills in the cache block with the values that succeed it. We're actually going to be getting a lot more hits. So what is that? And A is I times n plus j. So that will be our good spatial locality. So if we go back up, we have I times n plus j. And if you want to really easily get your stride, if you're still doing like lab 13, 14, if it's being multiplied by n, it has a stride of n. If it's just being added on, that means it's just being incremented by 1 each time, so it has a stride of 1. And if it's not even in here, it has a stride of 0. Oh, do I have to fill out the totals? I guess so. 2,000. Number of misses is 1250, which is something, all right. 2,000 divided by 1250. What's that as a decimal? There you go. That's what the calculator gave me. So that's what I'm putting down, 1.6. So do we have any questions on this? I feel like there are some parts I stumbled over.
I think for the miss rate for like the percentages I think for that one, like the answer key says like 0.63. I think they kind of want like the average for that one, I think.
The miss rate?
Yeah, like the percentage.
Is that so? Oh, okay. Where am I? So that would be well 50 or 125% divided by 2, which is 62.5%. Percent. There you go. So 62.5% is just 100% plus 25% divided by 2 for an average.
Nice. Okay. Now for question 10. Okay. So, alright, Charlotte.
I had a quick question about 9, but
yeah.
Yeah. So for in general for was it for the load for B? They were all misses. Was that because it had a stride of n essentially, or is my reasoning off?
Yes. So, having stride of n would mean it would overshoot the cache each time. So that's why it's always a miss. You should have seen something like that when you did your lab.
Yeah, that was in the lab. Yeah.
Okay. So for 10, CPU execution time and CPI is computed with the following time. CPU execution time and CPI is computed as follows when considering the memory access stalls. Damn. Okay. They give you this formula. Memory stall cycles equals IC times memory access over instructions times miss rate times miss penalty. To assume we have a computer where the clock clock cycles per instruction is 1.0. Memory access, hit time. Memory access, hit in the cache. The only data access are load and stores, and these accesses are 40% of the instructions. If the miss penalty is 200 clock cycles, and the miss rate is 2% for iCache, 5% for Dcache, how much faster would the computer be if instructions were cache hits? Memory stall cycles, would that include? Well, include the stall cycles for both instruction memories and data memory access. Dang, I can't read right now. That did not make any sense. Okay. So, they give you a lot of information. So, CPU, where everything is hit, is going to be IC times 1.0. And that's because memory access over instruction times miss rate times miss penalty is not important. So you just do times 1. So now we're going to fill out, so first we have to, this is with no misses. Okay, but now we need to figure out with misses. So we're going to follow the formula given above. So IC times, so we have 1.0, which is our CPI, times plus 1 times our fraction of, so we have our miss rate is 40% because we miss for the load stores, so times, actually no. Okay, let me restart. I'm not thinking straight. Okay, so we're given a CPI, or base CPI, which is 1.0, and the only data accesses are load stores, which account for 40%. So we have 40% of our instructions, which are load store instructions. The miss penalty is 200 clock cycles. Miss rate is 2% for iCache and 5% for Dcache. So first things first, we'll go over with this iCache and Dcache. So we're going to do our 40% times our Dcache, which is 5%, so 0.005 times 200, and this gives us our miss penalty for whenever we go to load stores. Now we also need to add that to our miss penalty for for any other type of instructions, and so that will be, I guess, so it would be 200 times 0.02, and then another, yeah, it has it as 1, but I feel like if the other one's 40, then this should be 60, so, but I'll do it as 1. And then all of that plus 1, which is our base CPI, times our instruction count. So if you multiply all of this together, or add all of this together, then you should get CPU with misses as IC times 9. So in a grand scheme of things, our CPU is 9 times faster without misses. So I guess that's all I wanted you to solve for. Cool. So that's it for that problem.
Can I just take a quick look at the number 9 spatial locality?
Yeah.
Please, thank you.
So you want the table, or do you want just this part?
No, I missed that. I wrote it wrong. I got it now. Thank you so much.
No problem. So any questions overall about this at the final? Nice. Tough crowd.
Well, thank you guys.
No
Appreciate
problem.
it.
No
Michael, get some rest. Go to sleep.
I will probably go right back to sleep after this. I think I slept like
Alright.
13 hours the last
No,
night.
you tough it out. Thank you so much for doing this, even once we appreciate it.
No problem.
Yeah, I really appreciate it, man.
Thank you so
Have a good
much.
night, guys.
Thanks, guys.
Good night, everyone.
Thanks.
I don't know.